Welcome to chapter 6 and eventually to chapter 7. This is a chapter about atoms and eventually moving into chemistry. So this is a really exciting chapter. We're going to first of all look at the structure of atoms and then look at radiation and how those atoms can break apart in awesomely powerful nuclear reactions. And then in chapter 7 we're going to look at some chemistry and exactly how it works on a more molecular kind of wet chemistry level. What you're looking at here is a highly stylized version of the atom. So you can kind of see the major points here. You can see there's the nucleus, and you can imagine that some of these would be protons and some of these might be neutrons that make up the nucleus in the middle. And these bright and shiny things here are obviously supposed to represent the electrons flying around the outside of the nucleus. This might be something you're familiar with. We probably talked about it last year in Year 8. So we're not going to talk too much about that a bit later. But what I want to look at right now is how did we reach this model? Because it is a bit abstract. Remember, we've never been able to view an atom like this. You know, this is very much a diagrammatical understanding of the basic building block of reality. How did we reach this decision that it looks like this? And the story is very, very old. And it's one that took us a very, very long time to get any kind of consensus on. If we have a look, this is what we're looking at here is a basic path to where we are at the moment with our understanding of the atom. But if we go all the way back to the beginning, we generally talk about a man, a Greek philosopher named Democritus. Democritus was actually one of a number of different philosophers dealing with a challenge, I suppose, by one of his colleagues called Parmenides. Parmenides really said something like, that change is illusionary. Okay, he was saying that we can't have something coming from nothing. We can't have there being nothing and then something created. Which is something that's an idea, that's a philosophy that we still agree with today. So Parmenides was saying, if we can't have something growing from nothing, then change must be illusionary. And this is what he means by that. So imagine you're looking at a seed. All right? You look at a seed and you put it in the ground and then it grows into a tree. All right? And he was saying, well, if we can't have something being the tree come from nothing, which is the seed plus more that makes up a tree, then what that must mean is that it must be an illusion that we plant seeds and we get trees, because it cannot possibly be that something has just come from nowhere. Because you've got to understand at this point, Parmenides had no concept of the idea of atoms and the idea of the smaller parts to make up the rest of the tree. Okay, so this was Democritus's great push forward in that he did suggest the idea of this tiny indestructible particles named atoms, and he suggested that when you see a seed growing to a tree, it was because the seed was soaking up atoms from the ground and then turning it into the wood and leaves and everything that you eventually see grow. And that in its basic core is pretty spot on with the money, and certainly dealt with Parmenides' challenge to the other Greek philosophers of this idea of change being illusionary. And we were quite happy with that for a long time. And there were some other advances along the way, but if we keep on moving along, we start talking about Dalton in 1808. Dalton's great contribution is not only that he agreed that there are tiny particles called atoms, and he also agreed that they couldn't be divided into smaller particles, but he started to say that atoms of the same element were alike. So he started to talk about the periodic table of elements, and he started to talk about atoms existing in whole number ratios. So H2O, being 2 hydrogens and 1 oxygen. It wasn't 3/4 of a hydrogen and 5/8 of an oxygen. The whole number ratios, which sounds very convenient, but it is just how it happens to have worked out. So that was a big push forward from Dalton. It was only 11 years later that we start talking about Thomson, giving a kind of a beginning kind of structure to how Thomson thought the atom might look. And this is kind of, if we have a look over here, this is kind of how he thought it might look, as in a big ball of positive charge, with it dotted with these little negative electrons, these little negative charges. So it was almost, it was nicknamed the plum pudding model, because imagine this was a big pudding with plums kind of stuck into it. And those are the ones that, have the negative charge. But on the whole, he thought it was a big positive ball of, atom. And this lasted, not very long, until we got the famous Lord Rutherford and his firing, various particles at various atoms and having various successes. And what he really suggested, his big claim to fame, is that he suggested, well, no, it's not just a big ball of positive charge. Actually, the positive charge is only right in the center. It's only in the positive nucleus. And he suggested that the electrons, the negative charges, weren't kind of embedded in the plum pudding, but rather were flying around the outside. And this is, now we're starting to look like an atom that we would recognize, right? We have the positive inner and the electron cloud on the outside. So this is pretty good. We're up to 1911 by now, so we're looking pretty much towards a modern view of the atom. This was an exciting time for physics. There was a lot of changes going on, a lot of moving into ideas of quantum mechanics and all this kind of stuff. So, one of Rutherford's colleagues, Niels Bohr, who was a hockey player, I believe. I think he played hockey for in the Olympics, something like that. I should back that up. Anyway, ask me in class if I haven't thought of it by then. Niels Bohr suggested, well, yes, that sounds good. We've got the positive inner and the electrons on the outside, but he suggested not only are there positive inners, but the electrons actually exist in what's called electron shells, or electron states. So the ones that are closer to the positive nucleus are on a higher energy state, and the ones that are further out are weaker and weaker and weaker, so that way you can get heaps and heaps of electrons flying around it. Okay, and that was pretty good. Again, this is looking closer and closer to what we expect, and then we're only really looking down into Chadwick, 1932, when we've got the discovery, I suppose, of neutrons. So we have the positive protons inside, and he's saying that there are some neutrons in there that have to make up the mass, because the nucleuses were too heavy to just be made up of protons. It needed that there was neutrons inside there to make up the mass that they were observing in their experiments. And he was very happy with the electron charges as well. Okay, and there have certainly been a few other changes since 1932 to our model of atoms, but that's the basic idea. So this is what we have now. It's the protons in here, and the neutrons, the ones with the neutral charge, the no charge, neutron, proton with positive charge, and then with the electrons kind of flying around the outside. Okay. All right, all good. So what I want you to do now is go to chapter 6.1. I want you to have a look at the blue words and copy them into Quizlet, and I will see you in class. Bye.